So I want to do a quick video on oxidation states because a lot of people have been telling me they've been having trouble with oxidation states. They don't exactly know when something's reduced or oxidized, and this is something that's going to be very important for the MCAT, just to have this down pat. There are going to be a lot of questions that will either test this directly or allude to it, and knowing this will be very important. So as far as definitions of oxidation and reduction go, you know that general acronym LEO says GR. L, lose electrons oxidized, G, gain electrons reduced, right? So LEO says GR. That's generally what we know. But when you have organic compounds with hydrogens and oxygens and all these other things going on, it's a little bit difficult to see where the electrons are moving. And this is very important in biochemistry as well. When you're talking about the electron transport chain, that's all redox reactions, right? Those are electrons that are being transferred from high energy electron carriers such as NADH, FADH2, down the ETC chain all the way to oxygen, which gets reduced to water, right? So this is the general rule here. This is a figure that was taken from my exam crackers, I think, chemistry book. As far as oxidations of carbon goes, and that's most likely what you're going to be dealing with, you can have oxidation states for sulfur as well. That's something that you might see, and I think I talked about that in a previous video with cysteine and disulfide bonds. So if you have two cysteine moieties, which have that R group with an SH at the end, you can take off two hydrogens, and instead of those two hydrogens, you can form a bond between those two cysteine moieties, and that would give you a disulfide bridge. But this only happens when you're in an oxidizing environment. So in the cytosol, you're not going to have that happen because the cytosol is a very reducing environment. So those two sulfurs need to be oxidized. They lose their hydrogens. And in that scenario, they can form disulfide bridges. All right. So the general rule that organic chemists like to use is that increasing bonds. So as you increase bonds to H, to hydrogen, so that's moving to the right, you're going to get a more reduced compound. Okay. And the reason for that is actually has something to do with calculating oxidation states. And the way this works is that carbon is generally not that electronegative of an atom. Okay, it all goes back to electronegativity. That's a huge concept for the MCAT. So carbon is not that electronegative, but when it is bound to something like hydrogen, it's actually more electronegative. So I think carbon's electronegativity is somewhere around 2.5, and hydrogen's is like 2.2. I'm not exactly sure. You don't have to know the real numbers. These are all relative numbers. But know that carbon is more electronegative than hydrogen. Okay? And so when that happens, this carbon will pull in that electron from the hydrogen and each one of those. And that's where you get that -4. So that -4 comes from, it kind of has 4 extra electrons. Not really. It's not, it's not an ionic bond, obviously. It's not even considered as a polar covalent bond because the electronegativity difference is very small. But it's enough so that you can say that this oxidation state of this carbon right here is -4 because it's pulling in the electrons from all the hydrogens. But what happens when you start adding oxygens? So we know that oxygen is a fairly electronegative atom, right? And so when we add oxygens, now this oxygen is going to steal electrons from this carbon right here. Okay? And I think, right, okay, so you have this carbon, which is pulling electrons from these hydrogens, but you have this oxygen, which is pulling that electron from this carbon right here. So you have a net loss of 2 from that carbon from here. So you had 2 go to that carbon, and now you're losing 2 to this oxygen, right? So this hydrogen donated an extra electron to this carbon, and now oxygen is taking up both of those electrons. So you go from -4 to -2, okay? And as you move down, and you can calculate this very easily. So carbon is supposed to have just 4 around itself, right? One from each, just one from each bond, right? 1, 2, 3, 4. It's supposed to have 4 electrons around it, right? When you add hydrogens, each hydrogen is going to donate an extra electron, okay? So now it's going to be, you're going to go from 0, you're going to count down because electrons are negative. You're going to go from 0 to -1 to -2, -3, and -4. In this scenario, you have these hydrogens donating electrons, right? Because the hydrogens are not electronegative, but you have this oxygen stealing those 2 electrons. So not only is it stealing that one that was originally given by the H, but it's taking one that came from the C as well. So you go from -4 to -2. And as you add more oxygens, right, you can consider this double bond kind of as being like an extra bond to an oxygen. So obviously that's not true, but you can think of it as being a carbon bound to 2 oxygens. And that would get a further increase in oxidation state for the carbon. And as you move down, eventually the most oxidized compound that we see is carbon dioxide, CO2. And this has important implications in terms of energy as well, because we know that that out of these 5 compounds, we like to think that methane has the most energy. And we know that because methane could be used as a gas that we can burn and do work with, right? CO2 is usually a byproduct of that. So we don't burn CO2. CO2 is a product of burning methane, right? So this methane right here is high energy, and this carbon dioxide is low energy. And this is kind of what happens in the electron transport chain. You have successive movements of electrons to lower energy states until you basically squeeze out every last bit of energy from its movement down. You're converting chemical potential energy into the movement of hydrogen protons down their concentration gradient to form ATP bonds, right? So just the general rule is the more bonds you make with oxygen, the more oxidized the carbon gets. The more bonds you make with hydrogen, the more reduced the compound gets.